Yeah, so hello everyone. This is my presentation on my INYPT problem, which is about counting matches. So this is my approach. So first we'll be understanding the problem statement, then I'll be talking about some background information, experiment overview, and the rest. So this was a problem statement which asked about how can we determine the number of matches in a matchbox from the sound it makes when you shake it. So basically, this problem statement wants us to shake the matchbox, but it does not mention how the way in which we should shake it. So that's why I have taken readings in X, Y, Y, Z, and X, Z plane for reference. So the properties of sound that I investigated was the frequency of the highest peaks of the sound spectrum and the corresponding decibel, like basically loudness of the sound produced. So this is done through the Audacity software on a laptop. So this is the background information that I researched. So first we talk about the independent variables which will be changing, which in this case is number of matches in the matchbox. Then the other one is the type of matchbox you are using. So for this experiment, I used two kind of matchboxes. The first one was an Apple matchbox, a company called Apple, and other one was Homelight. Then the dependent variables are decibels of sound produced, basically loudness, and the frequency of sound produced. Now the variables that I controlled was the volume of matchboxes. So basically, if I'm doing an experiment with the Apple Matchbox, so I'll be using the same matchbox again and again to make sure the volume is the same. Then I conducted the experiment in the very same surroundings. So if there are any background noises incorporated in one of the readings, so they are there in almost all of them. And so due to that, I'm able to rule out that factor of the surroundings. Then the third one was the materials of the matchstick. So we use the same material of matchsticks for all the experiments, which was wood. Then next is horizontal distance of the laptop from the ruler. So I'll show you a setup right now in which I put the laptop like near 6 to 9 centimeters from the matchbox in order to record the sound. Then height of the ruler from the stool. So basically, I kept my laptop on a stool, and and the distance of the ruler from the stool on which the laptop was kept was around 30 centimeters, and the horizontal distance was around 4 centimeters. Then the point of contact of force and the point of release. So point of contact was marked on the ruler, and the ruler was relieved from the height of the tables for every trial taken. So this is my experimental setup. As you can see, there's a cantilever. So in the cantilever, I have used a cantilever to make sure that the matchboxes are shook in the very same way for all the readings. I use a vernier caliper to in order to find the volume of the matchbox and the volume of the matchstick. And you can see my setup on the left picture in which there's a laptop around 4 centimeters horizontally apart and a little below the matchstick which is shaking. And there's the Audacity software in it which shows how the sound is recorded. So this is the methodology. So I use a simple apparatus involving a ruler clamped down to a table in between a sponge to minimize the sound of the cantilever when vibrating it. In the front end of the ruler, hanging out of the table, I attached a double-sided tape, to in order to fix the matchbox. Then I kept a stool next to the table, and on top of that, I neatly arranged around six tables on top of it. On top of the table, I place a laptop and open the Audacity software so that it can measure the sound as accurately as possible due to vibration of the matchsticks. The distance was kept constant as talked about before, and I took the number of matchsticks from 0 to 36. Originally, the sticks were not attached to each other, and when I collected data, I observed that even when the matchbox was almost full, the percentage of volume of empty space was coming out to be very large because of the spaces between matchsticks. Hence, I attached the matchsticks to each other using the glue, so that this was eliminated. This helped in reducing the experimental error and allowed me to obtain more accurate results. One of then After extrapolating the audio, I fed the data through a spectrum plotter and noted down the peak frequencies and amplitude values. After three trials with the matchbox of a certain size and a specific number of matchsticks in it, I changed the number of matchsticks and then the duration and then repeated the experiment. So I'll show you the phenomenon now. So this is a video. As you can see here, I release a matchbox and record the sound it's producing in the Audacity software as seen in the video until it's completely quiet. Yeah. So So this is the next slide. So I use Audacity software. So basically, I used a plot spectrum in order to get the highest frequencies and decibels of sound for the first 10 peaks. As you can see, there are 10 peaks, 10 peaks which were differentiated from the whole audio, and then I used plot spectrum in order to find out the highest frequency and the loudness. Then this is these are the values, and this is the way I done it for different numbers of matchsticks, different orientations, and different matchboxes, and this was the graph I obtained. So this graph was obtained of decibel versus number of sticks for orientations X, Y, and YZ. This clearly shows that loudness will increase till the optimum value, after which it starts decreasing. And this optimum point was around 16 to 20 matchsticks. And the bell shift curve made me curious to explore further as to why this change was occurring in such a manner. So this is a theory. I hypothesize that the sound needs a medium to travel, and volume of air inside the matchbox cannot be ignored by considering only the matchsticks in the matchbox. So this made sense, and because a fraction of empty space in the matchbox is more, the sticks will have more time to accelerate and gain speed and hit the opposite wall. With greater speed, there will be greater amplitude of vibration of the wall of the box. However, when we increase the number of matchsticks by a lot, the empty space reduces so much that loudness cannot increase with the increase in number of matchsticks. So that is why there needs to be an optimum value which shows the correct around the correct volume of empty space inside the matchbox and the matchsticks, so that we get the loudest sound. Then, thus, the purpose of the derivation of theory is to find relationship between the percentage of empty space and the loudness of the sound produced. So this is a mathematical derivation. So I wrote the function for acceleration with respect to time and integrated it two times in order to get the distance moved by the matchbox. Then the distance moved by the matchbox was equal to the empty space in the matchbox, which is how I arrived at the equation connecting distance, volume, and area of the matchsticks, as you can see here. Then, by equating the equations, I arrive at the equation connecting velocity of the matchsticks and the distance moved by the matchsticks, which is basically the distance of empty spaces in the matchbox. Then, because we know impulse is the change in momentum, but the final velocity of the matchstick is zero, as it decelerates to zero in a very small interval of time after hitting the walls of the matchbox. Thus, impulse is equal to mass of the bundle of matchsticks multiplied by the velocity of impact on the surface of the matchbox. Then the next step was obtaining the function for mass of the matchsticks by multiplying the density of matchsticks and the volume of the matchsticks, and then multiplying it by volume of empty box on both the numerator and denominator. By doing this, the relationship between impulse and the volume of empty space in the matchbox was calculated, as you can see in equation 4. Therefore, the force applied was proportional to the impulse, and the force applied is proportional to the amplitude of vibration of surface of the matchbox. But loudness is proportional to the square of amplitude of vibration. Since loudness is proportional to the square of force applied, loudness is proportional to the square of impulse, and hence the function between loudness and the fractional volume of empty space in matchbox was obtained as desired at the beginning of the theory. Hence the theory derivation using concept of physics was successful. So these are the raw data values which I got. It is for Apple Matchbox, Homelight Matchbox, their volume and the volume of and the effective volume of the matchsticks using thickness, length, and height. Then this was the raw data collection done for all different numbers, different all the different axes and the different matchboxes. And this is a more raw data collection. Then I eliminated the XZ axis for a reason, because if you take the length of the matchbox and vibrate it like this, then because the length of matchsticks remain the same, then regardless of the number of matchsticks, the amount that a matchstick can move remains the same. And that's why when we vary the number, because the space for the matchsticks to move is same, there's not much variation. Then these are the graphs I obtained for Apple Matchbox by plotting it in Logger Pro and by yeah by putting it in Logger Pro. Then this was a similar for Homelight Matchbox, which showed a connecting trend between both of them, thus strengthening the theory that it can be done for all the matchboxes. Then hmm, this is then yeah. So this is I also did this with Chewinghams to make to in order to identify if this is true for other items as well, and I got a similar kind of graph. Hence, this was my conclusion that because for both variations we get a Gaussian curve with the equation that was derived in the theory. Now, how will we determine the number of matchbox in an unknown matchbox? First of all, we'll shake the box in the XY orientation, measure the highest decibel of sound, and normalize it. We will find the percentage volume of space in the empty matchbox and repeat the same for YZ orientation. Because it is a Gaussian curve, we'll get two values for the number of matchsticks. For example, 10 and 20 for XY orientation and 12 and 45 for YZ orientation. Hence, the number of matchsticks in the matchbox would be between 10 to 12, and because the orientation doesn't change, the sound produced by a very large margin, as shown in the experimental graphs and data.